thank you for the entire team for taking the time out to really expose people to things that are taking place here in New Zealand and abroad regarding innovation and technology. So it's a very exciting time. Even under the particular conditions that we're in, it's still a wonderful time because what's taking place doesn't have to stop innovation. I think that that's very important that as we come out of this period, however long it takes, that there's innovation on the forefront to really make a difference in people's homes, in the world, as far as transportation is concerned, and particularly as far as energy is concerned, which I'll touch on a bit as well. So thank you so much for your time. And thank you, Kai. Thank you, Aruna. Thank you for the whole team. I really appreciate being here today. And so let me see if I can go ahead and click this share button again and go to the window that I had earlier. And if I can, then we're on and cracking. If not, then that might be a challenge. So I'll give it a go here. Talks with the do. I think this is it.
Share screen option.
Yeah, I see the share, but what I'm trying to find right now, I think this is it. Let's go with that. All right. Hopefully,
Looking good.
yeah, I think we are. So thank you very much. And basically, what aerospace is doing here in New Zealand and abroad is tackling really two challenges. One of which is the environment. So, in addition to climate change issues, it's well known around the world how there's an increase in the amount of plastics that are entering into our oceans, not just plastic bottles like you see here, but also microplastics as well. That fish are digesting, and then those fish and turtles and whole bunch of sea creatures are losing their lives, and then that affects the food chain for us as well, for those who eat fish and so forth. So there's really a worldwide growing problem as far as our oceans being increasingly polluted by us not making efficient use of the resources available to us. And one of those resources is plastic. So what you see on the screen here is a whole lot of polyethylene terephthalate, PET, and much of that could have been recycled, where we could do so many different things with all of the different technologies that are readily available to us. This is one of the challenges that is taking place, because in the Pacific, we have the Pacific patch. In the Atlantic, you have the Atlantic patch, and these are literally plumes of floating plastic, not the floating or other plastics that are underneath the ocean, but those that are floating that can be seen. That in of itself is a great issue. But then you have the Indian Ocean patch, you have the Caribbean patch. It's growing worldwide, and there's some efforts to tackle that. But I think one of the best ways to tackle that is prevention. So what can we use plastics for that can reduce the amount of plastics that enter our oceans in the first place? So that's one of the main challenges that aerospace as a team has been tackling. But there's another challenge as well, and that challenge is energy. So right now, this is a perfect example of, the amount of energy that is being utilized right now. Back in 2015, there was 22,000 terawatt hours of electricity being used, and a good part of that was in ICT. Now, as we're here on this Zoom conference right now, and as many people are in their homes and are making use of, not only, webinar technologies like Zoom and, entertainment consumption technologies like Netflix, people are doing more and more work online, internationally. All of this is costing electricity. And there's a growing amount of consumption where, as we see the Internet of Things increasing, as we see AI and all of these things that require all of this consumption of electricity, even present, there is not enough supply to fulfill the demand. And, we see in countries all around the world, New Zealand included, utilities companies that at times even fall short of the promised amount of electricity that is going to be consumed in any given year. So we see that in North America, South America, Africa, Asia, Oceania. So there's another challenge, especially as our population grows, is the additional consumption of electricity as many parts of the world also become more urbanized. So these are the two challenges that one we faced regarding the drop, which we'll touch on in a second, and the other one in regards to REPS Technologies that was developed by a gentleman by the name of Andre Williams, who is the Chief Technology Officer of REPS, which is a subsidiary of Aerospace. So in regards to the first challenge, people have asked me before, can a vehicle be 3D printed? And the answer is yes, because it's been done before. So back in 2014, there was a company called Local Motors that developed a vehicle called the Strati. And that vehicle is all electric vehicle, and they developed it two-seater, as you see there. And that vehicle, that body that you see in the screen there, is 3D printed by a 3D printer called the BAM printer. That's short for Big Area Additive Manufacturing. That was developed by a company called Cincinnati Incorporated. And so they did a fantastic job in developing this 3D printer that can be utilized to 3D print a vehicle. Now, the vehicle that you see there was made out of ABS plastic and carbon fiber, combination of the two. And in taking the idea of the drop, which is the vehicle that we've been working on here at Aerospace, we wanted to approach it a little bit differently. Can there be use of not virgin plastic, which is plastic that has not been used before, but recycled plastic? And I met a gentleman shortly after arriving to New Zealand in 2015 by the name of Chris Keenan. He resides in Devonport, and he's a 3D printing, 3D modeling expert. And we sat down, and he introduced me to pieces that had been 3D printed, small pieces, handheld, that were 3D printed from PET. And I was like, this is absolutely amazing. And he used a filament from a company called Inofil, which is based in the Netherlands. And, I thought to myself, well, if we're going to develop this 3D printed electric vehicle made out of recycled plastics, then we're going to need to utilize a method that is low cost. So the Inofil filament was quite expensive to develop, filament, and then ship to whatever destination around the world. So we had to use local resources in order to, make sure that what we were doing was, economically feasible and environmentally feasible. If you're transporting, recycled materials all around the world, there's a cost to that. There's shipping costs, there's shipping pollution that takes place. And, shipping pollution is one of the largest pollutants that many people may not be aware of. So if there's a way that we can use local plastics to 3D print vehicles or other items, for example, let's see how that can be done. And so in combination with a material that is widely accessible, that's naturally sourced as a hardener additive, that came across as the combination that we can utilize to 3D print the drop. So shifting gears, as we're talking about this environmental effectiveness of utilizing recycled plastics to 3D print, there's another issue as well in terms of even electrical use of vehicles, how that can add to the grid. So, if let's say the world right now immediately just transitioned from, petrol powered vehicles to electric vehicles, one, is there the infrastructure to deliver that electricity? And also, how is that going to impact the grid and utility systems? And is there enough energy in order to manage both, buildings, companies, homes, um, data centers, and electric vehicles at the same time? So when reps merged with Eurospace back in late 2017, a couple of months after the TED Talk that I'll share in a little bit, um, one of the real purposes in us merging is to make sure that the reps technology developed by Andre came to the forefront. Why? Because of issues like this. So um, in Dublin, for example, you have a certain amount of electricity that's consumed. Well, one of the data centers that was being built in Ireland by Apple, once complete, consumes more electricity than the entire city of Dublin. So, and that's just one company. There's data centers all over the world, and all of these data centers consume vast amounts of electricity. That's one of the reasons why, many data centers are in cold places because they're trying to reduce the electrical costs because heat and electricity, don't necessarily get along. The colder an electrical circuit is, generally speaking, the better it operates, the more efficiently it runs. So, these are challenges, worldwide that we have to address that are interrelated with one another, not just independently, but in how electricity can be utilized for vehicles as well. So back in 2011, I was giving a keynote talk because I was leading a team in a competition called the Cafe Green Flight Challenge to build an electric efficient aircraft, and the one that we were working on was a diesel electric hybrid. And I was asked to speak in Orange County. And at that event that was put on by Brian Haggerty, I met a man by the name of Doug Malowicki. And there were three keynote speakers at the time because the theme was super cars, super trains, and super planes. So I gave the talk on super planes. Another gentleman gave a talk on super cars, and Doug Malowicki gave a talk on super trains. He had developed something called Skytran, which is a monorail hanging, uh, basically pod that's maglev. So there's little friction that can transport, two people, for example, throughout a city that has this network of these elevated monorail tracks. Very efficient, awesome, and I was greatly inspired. He had been on the cover of, Popular Mechanics with this vision. And back in 1980, he developed a vehicle called the California Commuter that you see here. So the California Commuter is a one-seater, three-wheeled vehicle, two wheels in the front, one wheel in the back, that achieved the Guinness World Record for the most energy efficient motorway legal vehicle built in the world, achieving 157 miles per gallon. So I think that's about 66.7 kilometers per liter. Very efficient in its time as a petrol powered vehicle. And the following year, in 1981, he did the same thing for diesel, achieving 156 miles per gallon. And when we met at that event in Orange County, it was in Santa Ana, he said, "Wouldn't it be awesome to do an electric version of that?" And I said, that sounds like a great idea. Let's work on that together. And so that's how the genesis of the drop came to be. And here's a mock-up of what would later be uh, the drop in development. So right there, that's a fiberglass body that's on a metal chassis. And that the metal chassis that's underneath that is actually at our offices at Accelerating Aotearoa here in New Zealand, in Otara, at the We Otara STEM Learning Center that's organized by Judy Spate and Tony Marinovich, who are the founders of Accelerating Aotearoa, who invest so much time, energy, and resources educating young people, particularly in South Auckland, about science, technology, engineering, and math, and getting them excited about the sciences. So when my wife Sherelle and I first arrived to New Zealand, we met Judy and her husband because we were looking for an Airbnb, and that's how we met. So as soon as we arrived, we started doing volunteer work with Accelerating Outro almost immediately. Prior to that, this picture was taken in Orange County. That's Doug sitting in the seat there with the smiley face, head sticking out there. And to the left is myself. The next to me, the owner of the home where that mock-up was stored. We have Professor Joe, world-renowned oceanographer, and Al Timmons, who's a composite specialist. He's worked at SpaceX in Torrance, California. He's worked at the Air and Spaceport in Mojave, working with the Spaceship Company, who's responsible for the vehicles that are being developed by Virgin Galactic. You may be familiar with that company in terms of developing spacecraft for space tourism. So, it's just been a wonderful journey that I've been on, meeting these wonderful people in how we can evoke change in the future and inspire others to do likewise. Because in stemming, for example, plastics entering into our oceans, it's not one sole company that's going to accomplish that. It takes a team, and it takes a network of leaders being willing to step forward to come up with environmental solutions that can benefit our world and leave our world better than it was when we first arrived. And so here in New Zealand, met a gentleman by the name of Innocent Chikarema. He actually was a member of the same fellowship that we were attending upon arriving to New Zealand. And he's a 3D modeler. And what he did was he took the plans that were provided by Doug Malowicki, who is a consultant with aerospace, and 3D modeled them. So, these two-dimensional renderings, 3D modeled them into, what would be the drop. So you see the great detail and work that he did in terms of the suspension systems and the chassis. And what the 3D print is basically a monocoque of the vehicle, not including the suspension and the wheels and the batteries and the motors and the controllers and all of that. But the body itself is a monocoque chassis and body 3D printed together as a single piece. So that's the design, so that upon being 3D printed, it can be 3D printed in about 12 hours, utilizing a 3D printer that we're developing ourselves here in New Zealand. So going back to that BAM printer that I mentioned earlier for the Strati vehicle, that 3D printer costs $1 million. So, we came up with the idea, the aerospace team, to develop our own 3D printer at a fraction of the cost, utilizing an extruder from a company called Wegener based in Germany, and a gentleman by the name of Ben Blakey, who is one of the owners of a company called Imagine Plastics based on the west side, based, I believe it's in Avondale here in Auckland, has been working with us to modify these extruders that are basically handheld, meaning that they're lightweight, so that they can be placed on a gantry and moved utilizing electric actuators to 3D print with 3D printed dimensions of 3.5 meters long by about 2 meters wide and about 1.5 meters high, enough to more than enough build dimension to 3D print the drop. So, I submitted this idea to this competition, and this competition was called Next Visionaries, and it was put on by BMW and TED. So BMW-I, which is the electric innovation wing of BMW, and there were several hundred applicants. And in submitting about the drop, I was named as one of the top 6 to give a TED Talk pitch at the Frankfurt Motor Show in 2017. So, I'm very good friends with, the fellow speakers that you see here. And it was a wonderful experience where I had the opportunity to share about this vision taking place here in New Zealand to 3D print, whereby entrepreneurs around the world can develop their own aerospace franchise to have 3D printing take place on site anywhere around the world in micro factories, whereby the factories can 3D print these vehicle bodies closer to their respective markets. So anyone could go on the website, for example, order a drop, and upon ordering, it sends a notification to not only the 3D printer, but to all the other components manufacturers to direct ship straight to the customer to build their vehicle themselves as a kit. And so the vehicle was designed to have a range of, as you mentioned earlier, Kai, about 204 miles. That's 321 kilometers per charge. So, for example, here in New Zealand, upon its approval of being motorway legal, it is not motorway legal yet. So there's a long line of steps to work with the Low Volume Vehicle Technical Association before they would grant a certification whereby that certification can be taken to an AA, Automobile Association, and approved. And with that, someone can drive on the motorway to Hamilton and back on one charge. So that's the amount of efficiency, which is only consuming about 7.8 kilowatt hours. So to put that in perspective, a Nissan Leaf consumes about 50 kilowatt hours and does not have that level of range. So when we're talking about the efficiency here, one of the main reasons for the efficiency is how lightweight the vehicle is, only weighing about 150 kilos. I mean, that's about the weight of a motorcycle, but the vehicle's fully enclosed. And the vehicle, of course, has a greater amount of stability, being lowered to the ground, having three wheels. And of course, the aerodynamics, whereby it's rounded in the front, tapers to the back to have greater aerodynamic flow. So, and the third, and I believe the most important aspect of its efficiency is due to the REPS technology that helps improve the efficiency to help not only have that level of range, but even greater than that. So, we're being quite conservative right now in the range that we anticipate getting, but we're very excited about this vehicle and vision coming together in the near term. Now, there's questions upon, how marketable such a thing is. I mean, people are not necessarily used to driving a one-seater, three-wheeled electric vehicle made out of recycled plastics. Are people going to feel like they're in a Coca-Cola bottle? Who knows? We don't have the answers to that. But one thing that we're excited to do in the future is to, bring this vision to fruition so that people can, judge for themselves whether it's something that they'd want to uptake or not as a consumer. I think much more importantly, however, is the REPS technology that we're working on. And in my hand right there is actually the efficiency circuit in that pouch, where I had a chance to meet Dave Verma to my right shoulder there at a wonderful, wonderful company that is putting together automated minibuses here in New Zealand. So they've already had a showcase at Christchurch Airport, and they're doing amazing, amazing things. And some of the interns from the United States are there to my immediate left, and of course the gentleman to the far left there pictured is Stuart Little, who at the time was working with a company called National Instruments. So it's been a wonderful, journey, and that entity that Stuart worked for is actually the entity that did the first testings of the efficiency circuit. And this is what we're trying to address: the tsunami of data that can consume 1/5 of global electricity by 2025, just in data centers alone. This particular forecast, I actually believe to be quite conservative, because there's technologies to the forefront that require greater electricity. So, and this article, as you see there, was in 2017, but there's technologies now that utilize, data as data is a main driver more and more in society, where there's more and more electricity that's going to be required. So these are challenges that we're looking to address. I think LED lighting, which is a key focus of our technology that we're developing, is critical to reducing the electrical consumption of cities worldwide to literally 1/5 or greater than present. This can help get a handle on the consumption of electricity that I'm sure a lot of utility companies around the world are dealing with now because of the present situation pertaining to COVID-19. So, it's these issues that we're looking to challenge with the technology that you see here. So this is an older version of the efficiency circuit that we had tested, and we had later tested an updated version of that circuit at Independent Test Laboratories, ITL, based in Christchurch, just in early December of last year, after I had the honor of giving a talk at the M2 Magazine Success Summit here in Auckland. So basically, this particular version reduced electrical consumption to light LEDs, let's say a 100-watt LED, by over a third. So, for example, a 100-watt LED requires 29 to 36 volts to even light up at all. But utilizing the efficiency circuit, it was able to do so utilizing only 12 volts with no increase in amps. So that's critically important there, because if there's a lower voltage, well, somebody may think, well, maybe there's an increase in amps to kind of balance that out, but that wasn't the case. We tested and verified that the amp rating remained steady, yet illuminating an LED as it would require 3 times the amount of electricity to do. So, we're dealing with a huge challenge, and a little bit of the market here, you know, just to kind of put in perspective what a terawatt hour is, because I mentioned 22,000 or 26,000 terawatt hours earlier. To put that in perspective, a terawatt hour is 1 billion kilowatt hours. So, if you're at home and you're consuming, let's say, 10 or 20 kilowatt hours, 1 terawatt hour is what, 100 million times that much compared to 10 kilowatt hours. So 1 terawatt hour equals a billion. In terms of 26,000 terawatt hours, we're talking about 26 trillion kilowatt hours. That's major consumption. And, these are forecasted numbers that, as I mentioned before, are quite conservative. So, if somebody's consuming 10 cents, per kilowatt hour in your home, that adds up to $2.6 trillion in cost. So the updated efficiency circuit that I demonstrated at the M2 Success Summit literally consumes for an LED 1/10 of the electricity required for the LED to light up. So if we in homes can utilize LED lighting, which is, taking place all over the world. I mean, even, the home that I'm in right now, all of the lights are LED lights. So when we put that into perspective, we can considerably reduce the amount of electricity consumption around the world, and that's just in lighting alone. When we take a look at other applications, mobile devices, laptops, cell phones, electric vehicles, we literally have the potential to, reduce the electricity consumption around the world several fold, so that utility companies can get a handle on the electricity that they provide for their, customers, without having to deal with all of these fines that are being imposed to utility companies around the world for not meeting the standards that they have promised to deliver. So right here is I have a picture at Ormiston Junior College in Flatbush here in Auckland, where the older version of the energy efficiency circuit was at work. So there, right there, the student next to me, he's actually holding the 100-watt LED in glass that's filled with water. And the point of that was to share that the LED didn't short. So that's another feature of the efficiency circuit, that the electricity that's going into the 100-watt LED that doesn't have any type of coating or anything on it, it doesn't short, and the amount of heat that's generated is nominal. So a lot of people think that LEDs are quite efficient, that they don't generate heat. That's a misnomer. It actually generates a lot of heat on the back of the diode, because the LED is a diode followed by Andre and reps. We're able to deliver that electricity where the end application LED is at room temperature and is very, resistant to water, which usually doesn't mix well with electricity, but it does here. So these are some of the features that, we're very excited to share with the world. This is going to be the focus of aerospace over the next 5, 7, 10 years, to make sure that electricity around the world can be provided at much lower cost, utilizing much less, consumption than what is taking place presently. Um, there is, again, Stuart Little, and we were over at National Instruments. That was the first test, and you see the efficiency circuit, older version there as well. My intern, who is based in Christchurch right now, Nick, standing beside me, along with Yuan Chen, also of National Instruments, to the left there. So that was the first test, and the test that we did recently at ITL performed excellently. And here is, I think I have it with me here. Um, oh no, we go back to the picture earlier. So basically, this is what we're looking to bring. This is the contribution that we want to make to the world. It's been a journey that I think is really going to help a lot of people. There's so many places around the world that don't even have access to electricity. So many homes around the world that don't have access to electricity right now. But if we can bring efficiency, then those homes can have electricity utilizing solar energy, other renewable energy sources that do not require all of the time, energy, and resources that a grid requires in order to put in place for homes that are outside grid areas. So a very exciting time. And thank you so much. I don't know if I went over time, Kai and Aruna. Please let me know. I apologize if I did, Claire, but please let me know. And thank you so much for your time. I really appreciate it.
No, that was perfect. Thank you very much.
Thank you, Ira. It was fantastic.
It's a pleasure. Thank you so much.
Thank you.
Thank you, Ira. That was great.
So we have
you.
for questions, hey?
Yes. Question and answer session now. I think Claire wants to maybe manage this because she is the admin of the meeting. So raise your hands and we're good to go.
Yeah, so if you can use the raise hands option in there, and hopefully it will show on my screen who's raising their hands. If not, I'll unmute all and we'll have to be curious. Does anybody have any questions? There was a lot of information there, right? Are you connecting, Kai, with any universities at the moment for your research needs? Sorry, Ira.
Ira, can you hear?
Oh, what can you repeat the question, Claire?
I'm interested to know whether you connect with any universities at the moment for any sort of research needs for.
Absolutely. So pertaining to the drop, this is not a university institution, but we were so pleased to work with Manukau Institute of Technology, whereby over half of their engineering students, this was in 2017, 2018, all did their capstone projects in relation to the drop. So, it was a wonderful collaboration. And we're very excited to work with other educational institutions to further the technology, both on the drop side and also on the rep side as well. You know, it kind of, as I alluded to before, it's going to take a team to really bring these technologies to the forefront. You know, one small group of people can't do it alone. So it really takes a national and international network to accomplish that.
Right. Oh, well, I'd love to speak to you about that more, perhaps at another time.
Absolutely, Claire.
Kai, you have a question?
Yeah, right. So raise my hand. I found the feature finally. Okay. Hey, Ira, I have a question concerning the shape of the drop. So surely the drop is probably the most efficient in the wind channel. So the question is, do you actually do testing in the wind channel? And is the shape mainly dictated through the wind channel? Or is that, how did you come up with the shape?
Sure. The original shape is very much modeled by Douglas Malowicki with the drop. So if you take a look at the drop from the top, it almost is completely identical to the California commuter in size and aerodynamic shape. And Doug Malowicki, by the way, he's an aerospace engineer, and he did his calculations on the aerodynamic efficiency of the California commuter, whereby we were able to extrapolate that information, apply it to the drop, and see what efficiency gains we would get. And the results are quite outstanding. One thing that is interesting about the shape of the drop is that it tapers to the back. And somebody may say, well, maybe if you put the wedge to the front, wouldn't that be more aerodynamic? Well, the challenge with a lot of vehicles that are on the road right now is that hatchbacks, the air grasps on to the flat rear of the vehicle. So a lot of hatchbacks on the road, even though, they're purported to be very efficient, they're very inefficient because if they had a more aerodynamic design in the rear of the vehicle, they would actually have much greater efficiencies and there would be much less strain on their engines than present. So that's what we wanted to accomplish with the drop in terms of having what's called a laminar flow. So that means that the air around the drop stays along the body of the drop rather than, providing these areas and these pockets where vacuums are created, where the air gets stuck to the back. When you have laminar flow and the wind is able to easily breeze off of the rear of the vehicle, that's where you get your efficiency much more than the front of the vehicle. So yeah, so far the results are pretty good in terms of aerodynamic efficiency. We haven't put them in any wind tunnels or anything like that, but perhaps sometime in the future.
Right,
We
thank
have
you.
those. Rachel, would you like to ask a question?
Yeah, sure, thanks. Ira, thank you so much for sharing. What an amazing journey you've been on. And as a South Aucklander, I just want to say thank you for keeping some of that in the local community because it's well needed in our neck of the woods. Yeah, my question was, I've sort of worked across fast-moving consumer goods by plastic and actual collection of said plastic for recycling purposes has been quite a challenge over the years. What is sort of the mechanism for how you will actually gather and get the plastic into a position whereby you can actually utilize recycled plastic for these vehicles?
Absolutely. Great question. There was a factory that was closing down that made hangers in Glendine, which is in West Auckland. And I met this gentleman, his dad had passed, and they were closing down this factory. The siblings decided to sell it and so forth. And he said, there are tons and tons of recycled PET plastic there in flakes. Do you want them? And I said, yes. Otherwise, they would have just been, taken to the tip. So I was able to garner over 7 tons of recycled PET plastic flakes. And we have those saved for the drop. Now, in terms of a network, you're right. At present, interestingly enough, even in our recycling system here in Auckland and New Zealand proper, a good portion of those plastics do not get recycled. And this was before China shut down the intake of recyclables when they said no more. We're not going to be the garbage can of the world where you can just send us your recyclables and all of these other materials and we figure out what to do with it. They shut those doors. But even before then, I had received accounts, personal eyewitness accounts, where a lot of the recycling do not get recycled. They just go into the general rubbish in the transfer stations. So you're right. There needs to be a network whereby we can utilize these plastics in order to even prevent them from getting into the recycling system, so that they can be utilized for much better things. And which is why I'm very excited at several initiatives to help, with that. One of those initiatives is called Precious Plastic. And so basically, it's an open source system whereby people are given the plans to build machines to make use of plastics. There's a shredder that people can build themselves. There's an extruder where people can build themselves and utilize plastics for their own purposes. So I'm very excited, perhaps, to work with you on how we can ensure that some of this PET plastic that just gets mixed in with other recyclables anyway, it's actually quite difficult to, separate the plastics from everything else. There are processes to do that. I visited recycling centers in New Zealand where that is done. Visi is one here in Auckland. I went down to Smart Environmental just a couple hours outside of Auckland. Sat down with them in terms of their plastics there. But I'm very passionate about finding ways that we can utilize plastics, PET in particular, so that they don't get into the waste system to begin with.
Fabulous. Thank you.
You're welcome.
We have a question from Aruna.
Yeah, hi, Ira. I'm really, really impressed with the work that you're doing and with the STEM work with the school kids as well. That's great.
Thank you, Aruna.
My question is, what are your plans in the next few weeks? What's the next stage?
Absolutely. So I've sat down with several entities, and we're looking to have engagement regarding capitalization of aerospace to further the reps technologies. This is critically important, not necessarily for the drop as much, for improving efficiencies around the world due to the pressing issue of energy lack in many places around the world. Then, we're not just talking about, third world, we're talking about the West. So in terms of improving efficiency internationally, we're really focused on LED lighting and utilizing REPS technology to improve efficiencies in residential properties, commercial properties, and industrial properties as well.
Right.
And there's applications for REPS technology that are outside lighting, but that's the focus to answer your question in the next few weeks, as we have been for the past few weeks, that we're working on. So we sat down with many different institutions to help further that technology.
Oh, thank you. We do have a lighting department. I don't know if you know, I could introduce you to a few people at Massey University.
That would be wonderful, Aruna.
Yeah. And just for the benefit of everyone else, the next PDMA event or speaker is Rui Peng from Critical Design. I don't know if
Rui.
Yeah. So they do, they recycle plastic and make furniture. So that'll be interesting to listen.
Rui and the Critical team, they're awesome. I had an opportunity to sit down with Rui and Andy Crow over at Critical some time back, and we actually tested the plastics along with the hardener additive there using one of their extruders at Wesley Intermediate. So that was that was an exciting time. Wonderful work that Rui and the Critical team are doing as far as plastics and making wonderful use of it.
Yeah.
I can see Kai has and Rachel both have another question. I'll go for Rachel.
Sorry, I think I haven't turned mine off from the previous question.
Oh, okay. Shall we go to John Miller?
Sorry. Hi. Thanks, Claire. Hi, Ira.
Hello, John.
Regarding the drop, I have a couple of questions actually, but I'll go with one, and it's about load capacity. I'm thinking of its capacity for the carriage of goods as well as its driver, right, as potentially a delivery vehicle. So what is its, torque strength, or, well, load capacity, both in terms of weight and in terms of space for placing goods, whether it be a pizza or a bale of wool?
Yeah, that's a great question, John. So yeah, there's so many different factors and properties that we have to take into account as far as the material science for the drop. Torsional loads, how does the vehicle contort, given certain weight and where that weight is placed in the vehicle. The vehicle itself is so light that, the weight of the individual operating the vehicle actually has an impact on the performance because the vehicle itself is so light. So what we're excited about is the use of the additive manufacturing technologies to 3D print vehicles that are larger in scope, scale, and capacity that can be utilized as delivery vehicles, for example. So while the drop itself is not designed to be a delivery vehicle, it's designed to be a single person mover so that someone can, basically drive to and from work, for example. So it's not really designed to replace a vehicle. For example, if you have a two-person household, you have, let's say, a four-person household, and you have the two adults, and one might drop off the kids to school, something like that. In the larger vehicle, might that be an SUV or a standard size vehicle, the other adult might take the drop to work. So that was the design. So because of that, there's a minimal amount of space. We really took a minimalist approach with the drop. And the reason for that is because we wanted to improve its simplicity so that it can be easy to build as a kit, so that anyone under 20 hours or less without any technical expertise, you can have a sociology degree like myself or not have a degree, can put the vehicle together and understand how to do so easily, effectively, and safely. So there's not a lot of cargo space in the drop. There is some space behind the occupant, and there is some space to the left and right of the occupant to where you can put like a backpack, a purse, maybe a few bags of groceries, things of that nature. But it wasn't necessarily designed to be a utility vehicle. But the wonderful thing about additive manufacturing is that we can iterate quickly. So because of that, we can design larger structures which can handle the torsional loads for cargo.
Makes sense. Thanks.
You're welcome, John.
Great. Kai, did you have another question, or have you just not known?
Very quick one, I guess, because we're already almost over time. One quick question in terms of crash test and top speed. So I guess you have done maybe a little bit of crash testing. It's always the critical one. I've worked for Toyota before, and that was always a big challenge for us to make the vehicles as safe as possible, and then saving lives and making sure that you can also, the load is one big thing in the crash test, and what are the top speeds for those vehicles then? Because if you look at the scooters zooming around, they're actually quite fast, so you're sitting low on the ground. So it would be interesting to get a little bit of your insights on that.
Absolutely right. So the drop was designed to have a cocoon type strain. So even in it being lightweight, and God forbid a collision or an accident, the person wearing a 4 or 5 point harness would be relatively crash protected. The concern that we want to make sure that we address is making sure in getting it approved for motorways, not just here in New Zealand but internationally, is the process in order to do so. So as a kit vehicle, these come under different guidelines than a manufactured vehicle. This is one of the ways that we're able to innovate, because For example, there's certain things that a vehicle is required to have as a manufactured vehicle. Because of that, Kai, that really has impaired innovation, because there could be a level of simplicity that reduces the likelihood of malfunction,
Right.
reduces the likelihood of wear and tear. In a vehicle, in a standard vehicle, you have, hundreds of moving parts just within the engine alone. So you have likelihood of malfunction that, can cause an accident. Whereas with an electric vehicle, and particularly the drop and how simplistic it is, the drop is designed to have a rear hub motor. So the motor of the vehicle is in the rear wheel. You basically, as far as your locomotion goes, you have one moving part, and that's the rotor that's attached to the wheel of the vehicle. So because of that, we have a level of simplicity that, can help in terms of accidents and crashes and like things of that nature. But for a kit vehicle, it does not undergo the crash testing that
Right.
normally takes place for a manufactured vehicle, because it comes under kit vehicle guidelines. So we haven't done any type of crash testing of that nature. We first, in completion of 3D printing, have to 3D print the vehicle first, and find out what results we get as far as performance, as far as doing destructive crash testing
Yeah.
of our own accord, and seeing how those come out, making sure that we get the performance that we want, making sure that we get the safety levels that we're looking for. But
Right.
to date, there hasn't been any type of crash testing. I think the second part of your question was related to, you asked about.
The top speed, and like when you come to crash test, it always has to do as well, like with UV and all these things, you have to keep in mind, like how long does the shell last, things like that. But the top speed was the other question.
Absolutely right. So the top speed of the vehicle, we're looking to exceed 110, 120 kilometers per hour. So motorway legal speeds
Yeah.
is the designed and intended top speed for the drop. And you're right. If someone is going, twice as fast, for example, they can have, a 4 times of destructive impact, things of that nature. So there's things to consider in regards to the drop. And what we're hoping for is that in its simplicity, it comes off as very safe vehicle, where the occupant inside is cocoon straight protected. Of course, being a small vehicle, you have less distance from you to the outside of the vehicle than you would in a larger vehicle, such as an SUV, for example. We have tanks on the road, and interestingly enough, oftentimes, if you take a look at vehicles on the road, there's usually one occupant in it.
Mhm.
And there's studies that have been done that state that 90% of vehicles on the road, regular passenger vehicles, are usually only occupied by one person at any given time. And we have these massive tanks. What I'm excited about over time in terms of these SUVs that are like, so huge, is that in understanding the efficiency and simplicity, and also reduction in energy consumption in the manufacturing process that can affect the automobile industry, the automobile industry proper will uptake some of the additive manufacturing processes we're excited to showcase, whereby vehicles over time become lighter,
Yeah.
whereby there's not such a differential between the weight of the drop and the weight of other vehicles on the road. That's something that's going to be slow, ongoing process over time. But there's a lot of, vehicle and energy, critical thinkers over the world for the past 30 or 40 years that have been talking about, lightweighting your world as it is, that we don't need these, hunks of metal to drive around and to get from point A to point B. We just don't need it.
Great. Thank you for your answer, and thank you for the talk. I think we're already over time. If there are any other questions, maybe one more question would be possible. If not, we would wrap up. And
I think we're looking good to wrap up. Nobody else is raising their hand. So last chance.
if everyone just follows the link I've sent through, just submit your email and name to the email list, and you can be updated on the next meeting and who's going to be next and what exciting talks are coming up, and hopefully again as well in the future face to face. It's nice to do this right now here. It was a bit exciting in the beginning. I wasn't sure how it goes, but it went quite well. So I'm very pleased with the results, and I see we still have 11 people joining, and we I think had up to 17. So that was great that everyone joined. And thanks again, Ira, for your talk and for your time. And we hope to meet you all in person very soon.
Thank you again so much for your time and energy and resources put into this. Kai, Aruna, Claire, the whole team, thank you so much. I really appreciate it.